Is everybody doing all right today? All right. So today, let's see, I'm going to jot up what I'm going to talk about. So the first thing I'm going to do is actually talk about the group velocity and why it's called the group velocity, where that comes from. Then I'm going to sketch sound waves again. I'm just going to run through how we did it kind of briefly, just the highlights of how it works, how the pieces fit together, because there's a lot of pieces that go into this, but the pieces are kind of all the same every time you do a linearization process, so we're just going to touch on them. And then we're going to do gravity waves. And then I'll get into shocks. And we'll talk a little bit about shock waves. And maybe I'll put up some images because pictures are cool. Okay, so the first thing I'm going to do is talk about the group velocity. And why is it that we call it the group velocity? And where does it come from? So it comes from the basic, let's try. So all of our waves, our tiny little nugget of wave, our wave eigenvector is sine of kx minus omega t. And now formally these are vectors, but everything that we're going to do for a little bit is going to be one dimension. So keep in mind that k and x are vectors, but we'll treat them like scalars for a while. Sine of kx minus omega t. Or you can rewrite this as k times x minus vp t, where vp is just omega over k. We just factor out a k from this. And so we can see that this is just k times some phase. So this is the wavelength, or the wave number, and then this is the phase of the wave, and that phase of the wave changes both with space and time in this way, in that it translates with the velocity vp. So we're going to do the same stunt, but instead we're going to say, okay, now I've got a whole distribution of waves. This upper thing isn't real. This is just me drawing something so that I can make my wave packet make sense. So this is a wave packet that's got a start and an end, and some waviness in the middle. So this is just a superposition of waves that makes a bump. Lots of things do this. So I'm going to write down, we could write this down as, say, a density of x and t, or we can write it down as an amplitude in Fourier space, an amplitude of k and omega. So we're going to say that this amplitude is peaked at k naught and omega naught. So some value of k and omega are special. That is the dominant frequency. So this is like if you're listening to the radio, you're listening to an FM radio station. FM stands for frequency modulated, and oh crap. Oh, never mind. Nikhil will be late, and I have an appointment. So we have some wave packet that's basically peaked around some k naught omega naught. So like if you're listening to WVFS, which is the best radio station in the country, I shit you not, it is the best radio station. I've never heard a radio station that was willing to play such un-radio friendly things at 5 o'clock during rush hour. Like they played Einstein on the Beach, which is this magnificent minimalist opera by Philip Glass. So anyway, they played all of Converge's Jane Doe, which is like 11 minutes of blistering metal. I love this radio station so much. And then they play Kanye West. It's like my favorite. So anyway.
What'd you say it was called?
WVFS, the local radio station here, 89.7.
The one people have stickers of.
Yeah. It's the campus station, and it's been good the whole time I've been here.
Sorry, what's rho?
Rho is just my amplitude, or whatever. So this could be my density amplitude, so this could be my density. It could just be the amplitude of the radio wave power that I'm receiving. So when I'm receiving radio wave power, I'm getting mostly a frequency at 89.9 megahertz. But that frequency is modulated around that main carrier frequency to give us packets of waves that we can then interpret as sound. So we have a wave that's got some shape because it's not constant in k. If there was just one value of k naught and omega naught, it would be a wave that travels forever in all directions in time and space. So it's not a constant, it's not exactly one frequency. We have some other frequencies. So we're going to write down, I'm just going to call it some amplitude f of x and t. This is just because this is more general than just sound waves in water. This is true for all kinds of waves. So electrical impulses on a wire, and brain waves, all kinds of waves have the same kind of thing. So I'm just going to call it f of x and t, and we'll just be in one dimension now. This is just equal to a of k and omega e to the I k x minus omega t d k d omega. All I've done is written down the Fourier transform. So this is the Fourier transform of some amplitude a, right? So now we're going to take, let's think about doing a Taylor series of this whole thing around a and around omega and omega naught, k naught and omega naught. But actually, let's just think about this. Let's just think about, we're going to write k equals k naught plus k prime, and omega equals omega naught plus omega prime. I called them 1 before. I'm going to call them prime now. It doesn't really matter. So this is my tiny little deviation, and this is my other tiny little deviation. So we're going to, sorry, the squirrels started having a party and talking about other things. Now I got to go to my notes so that I remember how it's actually supposed to work. So I'm going to write I k x minus omega t as equal to I k minus k naught x minus omega naught t plus I k naught x minus omega naught t. All I've done is added 0 in this complicated way. So I've taken I kx minus omega t, and I'm trying to rewrite everything as k minus k naught, so deviations around my background solution. But I'm going to rewrite it like this. So this is what I've got. I'm going to write it like this. It's just the same thing. If you add this up, this cancels this cancels this, I'm left with the same thing. So I haven't actually done anything. And then I'm going to say that omega minus omega naught, here's where the actual linearization comes in. We're going to say that this is a function of k. This is k minus k naught times d omega dk. So this is where the magic happens, is making this assumption. I'm going to assume that I can Taylor expand omega as a function of k, because omega and k are related. That's what the dispersion relation tells you. So we go through all this math. We go through a bunch of math. On Thursday, we're going to go through a bunch of math again today for surface waves. You get a relationship between omega and k, and that's encapsulated here. So now I'm going to take this kind of more complicated expansion. I'm going to replace this omega minus omega naught with my k expansion, and I'm going to just expand everything out. and I'm left with f of k, f of x and t is going to equal to, so k naught and omega naught are constant, so I can take them out of this integral, and then so I'm just going to plug this into here and rearrange a little bit and take the constant stuff out. So then the constant stuff that comes outside is e to the I k naught x minus omega naught t times the integral of a of k and omega e to the I k minus k naught x, I ran out of void sticks, minus, sorry, k minus k naught x minus d omega d k t. So I'm just rearranging terms a little bit. And the place that the place where I pulled the stunt was expanding omega minus omega naught in terms of k. So I've got this relationship between omega and k that's we're just assuming is linear in the first derivative of omega. So now I haven't done anything interesting, but now I'm done. So now what I see is that this is now this guy, which is a wave with a frequency k naught and a wave number omega naught. Fix that up in post. A wave number k naught and a frequency omega naught. And then this other crap, which is a Fourier transform of stuff, but its behavior is up here at the top. The behavior at the top is k minus k naught times x minus d omega dk t. So this thing is a wave with a wavelength k minus k naught. And remember, this is inside, this is e to the all this crap. So this is all inside a sine function or a cosine function. Or an e to the I is really what it is. But sine and cosine you have more intuition for. So this is sine of some wave number, k minus k naught. And so that's going to be small because it's the difference. And then x minus d omega dk. This is the speed that the overall envelope travels at. So this is the speed that's going along with a of omega and k. So the amplitude, so that the envelope, that's this a, is going to travel with this speed d omega dk. Does that make sense? Maybe a little bit? No? Where did I lose you? Let me back up and try it again real quick, and then I'm going to probably assign it as a homework problem because it's useful. So we've got my Fourier transform f of x and t equals the integral of a e to the I kx minus omega t dk d omega. All I'm going to do is split this apart so that I've got some k naught and omega naught, and then I've got k minus k naught and omega minus omega naught. So I'm going to split it into the main frequency that the packet is traveling with, and then the frequency that the deviations around that main frequency are traveling. So this is like if you're on a train, the train has some velocity. You walking up and down in the train has some other velocity. So this is you walking up and down in the train. Not you walking up and down relative to what's outside, because there you're going, 60 miles an hour or 59 miles an hour or 62 miles an hour. Inside the train, you're going 1 mile an hour or minus 1 mile an hour. So that's this part. This is relative to the wave carrier, and this is the wave carrier, the main wave carrier itself. So we take this bit and we expand it so that it's k naught x minus omega naught t, because this is my primary, this is the argument for my primary wave, plus k minus k naught x minus omega naught t. So I'm doing this all in this up here, so this is going to be sine of all of this stuff. But that just turns into sine of k naught and omega naught times sine of delta k, delta omega. So this, because this is in the exponent, these are just multiplying each other. Let me do that a little better. I'm going to take this and plug it in here, and that's going to turn into sine of k naught x minus omega naught t times sine of k minus k naught x minus omega naught t. Because the exponent turns the adding into multiplying. That makes sense? So we can see this as a primary signal, and then the thing that's modulating that primary signal. When you multiply two sine waves together, they modulate each other, right? So this is what I want to do. I want to expand this into a primary sine wave and then a secondary sine wave, a modulating sine wave. Okay, really I need to do that in the E. So really we need to replace these sines. I did it with a sine because that's intuitively useful. Really it's sine plus cosine, so this is the exponential of this, and then I need an I. Does that make sense what I'm trying to do? I'm trying to split this wave into two pieces. So now, so we can see, just when I'm doing this, we can see this part. This part is my primary wave, and it's going to travel at this speed. And this part is my secondary wave, so we just need to have a better explanation of what this is going to travel at. So I know this one is omega naught and k naught are both constant. So when I ask what this speed is traveling at, it's traveling at a phase speed of omega naught over k naught. And that's constant. It doesn't change with omega or k. But this one, this is more complicated. So we're going to replace omega minus omega naught. We're going to say that this is k minus k naught times d omega dk. All I'm doing is changing variables. So this is just dropping down some chain rule, right? So I'm just changing variables from omega to k, and this is how omega and k are related. So then in this second term, so this term is constant and comes out. So this term comes out of my Fourier transform and is just a wave. So this is just sine and cosine of k naught minus omega naught t. And then this is the amplitude. This is the kind of outer packet. Hey, you made it. And it's traveling at this other speed, which we're going to call k minus k naught times x minus v group t. And v group is equal to d omega dk. So this part travels with this speed, because that's what this part of the sine cosine does. And this one travels at the phase speed. So when I look at the combination of the things, then this travels with a peak of the shape of the Fourier transform, and this just travels with the speed of the wave. So if you remember the GIF I put up the other day, where you've got a wave and it's got some bumps, the group velocity travels with the peak of the bump, and the phase velocity travels with the peak of the wave that's inside that bump. Because the wave that's inside the bump is the main carrier frequency, and then the shape of the wave is the perturbation to that carrier frequency. Does that make sense? Does that make any better sense? Thanks. Okay. That'll come back again, but not a ton. So now you've at least seen where group velocity comes from. The important thing, I'm not going to ask you to be able to do this derivation. It might show up in a homework, but it probably won't show up on tests. But I really do need you to know that the group velocity is the shape, and it goes like d omega dk. And the phase velocity is a peak, and it goes like omega over k. Okay. Does anybody have any questions about that? Everybody all right? This is one of the harder things to get your head around. It took me a minute. Now we're going to do, I'm going to do shallow water equations, because I spent a bunch of time with talking about dispersion relations, but I didn't show you a non-trivial dispersion relation. We did sound waves, which So actually, I'm going to recap sound waves. I'm going to do it over here. Is this on the?
How far do I get to go? There we go. Okay.
So to derive sound waves, we started with some equations. For us, it was continuity and the Euler equation. The second thing we do is we find a background solution. Find a solution that I know that satisfies the equations. 3, linearize around that solution. And that's as simple as Q plus Q naught plus Q1. Put that in everywhere and throw out any Q1 squared terms. Throw out non-linear terms. Then we do a bunch of algebra. And that's algebra that's unavoidable, but there you simplify the thing so that you can get it to an equation that you know how to solve. Since we linearized it, you're going to be able to solve it with exponentials. But this algebra is just sanitizing everything so that you can actually solve the equation. But it's going to be e to the something. Because I made it linear, it's going to be e to the something. I'm going to have solutions that look like dq dt equals something times q. And I know how to solve this. I know that that's an exponential. And maybe that exponential turns into a sine and cosine and oscillates. But it's still an exponential. It's still the same differential equation. And the fact that it becomes something that looks like the time derivative equals something proportional to q comes from the fact that we linearized it. So in the linearization process, you're throwing out all the things that make it hard. Then you do a little bit of algebra. Then you do the Fourier analysis. And with the Fourier analysis, what you're really doing is you're just going to swap d by dt equals minus I omega, and d by dk equals ik ik. So you're just trading the derivatives from each other. Okay, that's not actually what you're doing. What you're actually doing is you're plugging in something horrible and then magic happens. But the upshot is that because everything is going to be exponentials, after you differentiate, you're left with a thing, and then everything cancels out. And you're left with just time derivatives turns into I omega, and space derivatives, should be an x. Space derivatives turns into ik. And that comes from the fact that everything, all of our space and time information is now packed into this term. There's an amplitude term that tells you how much of each amplitude of each frequency you have. But this is what tells you actually how they behave in space and time. And when I differentiate this with space, I get ik, and with time, I get minus I omega. So you don't have to go through that process. You just need to write down k's and omegas. And then 6, you get a dispersion relationship. And this is really the ultimate goal. So this is omega of k. So we're going to get v phase is omega over k, and v group is d omega dk. And those are the things that we're actually looking for. So let's do something. So with sound, we start with d by dt rho plus div rho v equals 0. And d by dt of v plus v dot grad v equals minus 1 over rho grad p. So now we linearize it, where we're going to send rho is equal to rho naught plus rho 1, and v is equal to v1, and v naught is 0, v1 is small. And I'm going to do the Fourier analysis here too. So I'm going to swap all of these k's, all these i's with k's, and all of these t's with omegas. So the d by dt turns into minus omega. This rho is going to turn into a rho 1. Plus this is going to be just d by dx of rho naught v1. All the other terms go away because they're small. And this d by dx turns into plus I k equals 0. And then the other term, this term becomes minus I. Oh, I got an I everywhere, but we'll divide through by the I. Becomes minus omega v1 plus, this term goes away because it's nonlinear, because it's a square term. It's just the only thing we're left with is v1, v1. And then this term, we're left with 1 over rho naught plus d by dx, which turns into an ik, and we'll get rid of the I, rho 1. And then we need a c squared to get rid of the p. Did you ever follow all that? I just said a whole mouthful at once. I did it all slow in the last video. And then we combine these two things. So I multiply by a k here and an omega here, and I'm left with omega squared rho 1 minus c squared k squared rho 1 equals 0. So I spent a whole lot of time on it last time. This went a lot faster because I just waved my hands and did a lot of stuff in my head, but you just get the idea of the basic progression of things. So we start with our equations. We linearize, throw a bunch of crap out, and then we know that we can use Fourier analysis because we linearized it, and then we're left with our dispersion relation. Does anybody have any questions about that basic process? It all makes basic sense, and you feel like you could do this again for homework or maybe on a test? Because this will show up again. Okay, let's do it with a non-trivial boundary so that you can see where a real dispersion relationship comes from. So now we're going to work on gravity waves. This is different from gravitational waves. And this is getting harder and harder to Google now that we've actually observed gravitational waves. That was almost a decade ago now that we've seen gravitational waves. I didn't think it was ever going to happen. So a gravitational wave is bending of space. A gravity wave is a wave that's driven by gravity based on the height of the water. So I have water, and it has some surface, and it has some depth d. And what I'm going to do is I'm going to pick a little bit up, which means I got to pull a little bit down from next to it, and then let it go. And so the pressure is going to be some equilibrium pressure. So first thing, what are my equations? So my equations, the only thing that I need to worry about is d by dt of v plus v dot grad v equals minus 1 over rho grad p. So this is my equation. I might need continuity as well. It'll come out. We're going to linearize it around a background solution. P equals P naught, and V equals 0. And then we're going to pull another stunt where we're going to use potential flow. So here, because, okay, so first, curl of V is constant. No. Curl of V integrated over some surfaces that can move with the fluid is constant. But if I start with a fluid that has no vorticity, and I don't do anything that produces vorticity, namely this doesn't have a dissipation term, so I can't produce vorticity with this equation because there's not a dissipative term. So I can't make new vorticity here. It's only conserved. Because of this, I can say, just like gravity, I can say that V equals minus grad phi. We talked about this a little bit in the reading, but I'm going to do it now. Now we're actually going to use this technique. Most of what I'm going to talk about is some algebra and potential flow stuff. But we're going to go through the same basic idea. I'm going to take this, I'm going to linearize it, I'm going to do a bunch of algebra, and then I'm going to do my harmonic analysis. And then I'll get a dispersion relationship. But applying the boundary conditions is a little fussy, so we'll do that. So, okay, V is minus grad phi, so phi is my potential. I'm going to write this up over here. V equals minus grad phi. So what that means is that Vz is equal to minus d phi dz. Does that make sense? So derivative of phi in one direction gives you the velocity in that direction. That's how we define phi. Forgot to go over the reading questions, but the reading questions are all on shocks. So we'll talk about that in a second. Let's do this first. Also, I know, because of this, that del squared phi equals 0. Because I know that the divergence of this is 0. So if I take div of that, the divergence of the curl of the gradient of a scalar is 0. So these are useful things that I'm going to know. The other thing we need to talk about is our boundary conditions. So our boundary conditions say that at the surface, sorry, let's talk about the surface real quick. So what does the surface look like? So my surface is going to have some nice ripply undulating wave, and it's going to have some height, c. And I kind of hate this letter, c. It looks like that. It's a z or an x or something. I don't know. But for some reason, it's always used in this particular scenario for the height of the wave. So what I know is that when I raise this up a little bit, my pressure is going to be P naught plus P1, which is my my perturbation, minus rho g c. Why can I say that? Because if I prick this up by a little bit, by Bernoulli's equation, I just lose a little bit of the gravitational potential. Does that make sense? So rho gz is the gravitational potential energy density, and I'm trading it for pressure. You can see this in a couple of different ways. So if you look at if you call this a hydrostatic problem, then I'm left with, sorry, I needed gravity on here, plus rho g. So my pressure is going to look like this. My pressure is going to be P naught plus P1. So this is the sound waves that travel in the fluid, and this is going to be the surface, the actual surface wave. So our boundary conditions are at the bottom. At the bottom of my wave, what can you say? At the bottom of the ocean, what can you say about the velocity? It's 0. It's 0 into the ocean because you can't penetrate through the ocean floor, and it's 0 across the ocean because of the no-slip condition. Now that's 0 across the ocean just at the bottom, so immediately above it, it gets non-zero. So at the bottom, Vz equals 0, which we're going to say is minus d phi dz, evaluated at minus d. And then at the surface, the height of the surface is measured by c. So Vz at the surface, at z equals 0, is equal to dc dt. And this is also equal to d phi dz at the surface. let's see. So my linearized equation, so these are my boundary conditions. This is a thing that I'm going to use, which we wrote down up there. I'm going to need that for a second. I'm going to need my picture for a second. So my linearized equation is going to be rho naught d by dt of v1 equals minus grad p1. Okay, I've done the linearization part already, thrown out, so we're assuming, so this part gets a v1 because it's all by itself. This part goes away because there's two v's. So it's good, this is gonna be small because this is linearized. This part is my pressure, which I'm gonna write that way. Actually, let's just write it like that because I don't need the G. So, did I skip a step in my notes? Oh yeah, also at the surface, I did skip something. I skipped something here. Also at the surface, we can say that the fluctuating pressure is just going to equal to rho g c. So this is my deviation in my pressure is just going to be rho g z. So we take this, and we take this, and we plug this in to here, and we're left with d by dt of P1 over rho g equals minus d phi dz. And then we plug in P from over there, and we're left with d by dt of d squared of 1 over g of phi equals minus d phi dz. Okay, so we've linearized things. We've taken our boundary condition, and we've plugged everything in, and we're left with just this equation for phi. So now we need to, so this is the thing that we're going to work with. So now for a minute, it's just a boundary condition problem. So I'm going to assume, let's see, what else do I need? Oh, I also know that because of this, I know that del squared phi equals d phi dx squared plus d squared phi dz squared. This equals 0. I'm going to need this in a second. So I'm going to assume that phi is going to be equal to some phi naught e to the I kx minus omega t e to the k z z. I need a plus or minus on that. So this is a kx omega x and omega t, and a plus or minus kz z. I forgot to draw my coordinate system. X is that way, and z is that way. So we're doing the same Fourier stunt, except now because of the bottom boundary, I'm not going to have necessarily waves that propagate into the bottom. So we're not going to call this an IKZ, we're just going to call this a KZ. Because we linearize the equation, I've got derivatives that just depend linearly on the thing. So I can just look at this, and this is a linear derivative of phi, this is a linear derivative of phi. The answer has got to have some exponentials in it. Yeah?
So what's the 2
Where? This?
Yeah.
There it is. I took that equation, I took this equation, and this equation, and I get a square of that because there's a t on that. Okay, so now we're going to assume that phi. So here is a stunt that's used pretty regularly. we're going to say that phi equals e to the I kx minus omega t times a e to the plus k z plus b e to the minus k z. Oh, actually, okay, so this should be a kx, and this should be a kz. But I have this equation, so I can say that d squared phi dx squared plus d squared phi dz squared equals 0. This is just going to be kx squared times phi, and this is going to be equal to kz squared times phi. And the phi cancels, so kx squared plus kz squared equals 0. So kx, then you need an I in there somewhere. So kx has got to equal kz. Kx equals kz. Because of this, because my k variation has to equal my my x variation has to equal my z variation. So when I'm doing all of this, I don't need to worry about a kx and a kz. They're equal because of Poisson's equation. Does that make sense? Somewhat. Let me back up a step. So I have this equation, phi. So this is the equation that we're going to solve. We're going to solve it using something like this. So phi has got to equal to e to the I kx omega kx x minus omega t times e to the plus or minus kz z. So when I'm doing my Fourier analysis, vertical and horizontal, when you're starting out, can be different. So I have a separate kx for the x component and a separate kz for the z component. But when I plug this into Poisson's equation, that just shows me that kx equals kz. So we're just going to call that k from now on. Does that make sense? So from this guy, I get to set my two k's to the same. So now we're going to say, let's expand this a little more. So we have phi equals e to the I kx minus omega t times a e to the plus k z plus b e to the minus k z. So now we're just going to apply our boundary conditions. So our boundary conditions say that, and I should have erased them. So at the bottom, d phi dz equals 0 at z equals minus d. And at the surface, d phi actually, that's all I need. Yeah. So we use the boundary condition at the bottom. So I take the derivative of this with respect to z, and I pull down a k and a minus k. So this becomes e to the I kx minus omega t times k a e to the kx minus k b e to the minus k, or z. And this has got to equal 0 because of the boundary condition. Sorry, not phi. This is d phi dz. So I can say that this part has to be 0, so that I can say that v equals a e to the minus 2k z d. Oh, this is evaluated at z equals minus d. And that gets a plus. Right. No, e equals minus. Okay, so what did I do? Where did I go? So I start with my equation. I'll linearize it. I apply my boundary conditions on P and V, and I combine those two equations, and I'm left with this equation. And then we try to solve, now we're trying to solve this equation. We're going to solve this equation by assuming it looks like e to the I kx and an e to the kz's. So we apply our first boundary condition at the bottom, and we're left with this. And so now I can say that phi equals e to the I kx minus omega t. A comes out front, and then here we're just left with e to the k z plus e to the minus k times z plus 2d. This is phi. So now I plug this into here. All right? So I haven't used my linearized equation yet, so we'll plug this into my linearized equation. And then the left-hand side is 1 over g times the second derivative of phi with respect to t. And so the left-hand side gives me a omega squared over g. The g comes from here, and the omega squared comes from my two derivatives. And really, you get a minus sign there. Times e to the k z plus e to the minus k z plus 2d times e to the I k x minus omega t. So this first term is just plugging this phi into the left-hand side. And then I plug this phi into the right-hand side, and k's come down, and I'm left with a e to the I k x minus omega t times e to the k z minus e to the minus k z plus z d. Okay, this is kind of awful.
Could you write that bigger?
Yeah. Because we're almost there. So this comes to a omega squared over g. So the omega squared comes from the time derivative, and the g comes from the equation. And then we're left with the rest of the stuff itself. E to the I k x minus omega t. And then e to the z k plus e to the k times z plus 2d. Okay, this z plus 2d comes from the bottom boundary condition. So this is the left-hand side. And then the right-hand side is just d phi dz, which is going to equal a again, and then e to the I k x minus omega t times e to the minus e to the z k minus e to the minus k e to the minus k z plus 2d. I think I dropped the minus sign on this one here. Okay, so when I take this time derivative, omega comes out of the first one. When I take the space derivative, a k is coming out of the second one. So I've got a k here, and a k here, and a minus k here. And then, since this is true everywhere, I can evaluate this at z equals 0 at the surface. Does that make sense? So I evaluate this at z equals 0, and this turns into this turns into 1 plus e to the minus k z d. Sorry, 2d. That's a 2. And this term turns into k e to the z k minus k. Oh, that's a 1. Minus k e to the minus 2d. Okay, so I've got a 1 plus e to the 2d. Sorry, there's not a k. Oh, there's a k there. K there. I got a 1 plus e to the k2d equals 1 minus e to the k2d minus. I can rearrange this. I can say that, so let's see. The a's cancel, and I'm left with just omega squared over g. Okay, I've said this several times before. Watching me do algebra at the board is boring as hell. So what did I do? So I linearized this to get this equation. I applied the boundary conditions to get this equation. We applied the boundary condition. We made an assumption about Fourier analysis to get this equation. We applied our boundary conditions to get rid of to set the constants here. We applied the boundary condition and plugged it back into our main equation to get this equation. Apply that at KZ equals 0. So there's a little bit of algebra that you have to do to make all the things do what you want. But the basic physics is linearize so that all the hard and gross terms are gone. Do a little bit of algebra, and then you're left with this. What is this? So this is this I can rewrite as omega squared equals g tan h of kd. Because tan h is e to the x plus e to the minus x, no, minus e to the minus x over e to the x plus e to the minus x. This is what hyperbolic tangent looks like. And that's what I have here too, right? I've got a 1 plus e to the 2, so you just multiply by an e to the 1 and then divide, and you're left with just a tangent. So, because of all these boundary conditions, I introduced all of these changes to the equation so that when I get down to the dispersion relationship, now I've got this very non-trivial dispersion relationship. Now omega squared equals g times the hyperbolic tangent of k times d. And the boundary condition is in the problem. D is the depth of the ocean. So now we can talk about two different limits of this. Where am I ready to go? So what are the limits of this? So I've got omega squared equals g tan h of k times d. So if k times d is small, then this becomes omega squared equals gkd. And then the phase velocity, if v phase is omega over k is equal to, I bring a k over here, no, I divide through by a k squared, and I'm left with omega over k is the square root of gd over k. So now my phase velocity depends on k. So different waves of different sizes travel at different speeds. And you get a similar expression for the group velocity. And it's because of the boundary. Now in this limit, this is the deep water equation. So this is k times d is small. That means the depth of the ocean is small compared to the wave. And that's dispersive. Even though the boundary needs to be there, you're also saying that you're far away from it. If I say that k times d is large, what does hyperbolic tangent do as the argument goes to infinity? It goes to 1. So then we're left with omega squared equals just g. So then omega over k, omega squared over k squared, is just g times h. Wait, I messed something up. Yeah. That's supposed to go away. Pardon me. Let me cheat. Oh, I missed a k. Sorry. There's a k here. There's a k on this one, which I missed. So when you do the series, let me back up. Cut that part out of your brain. Just did that. So we're left with omega squared equals gk tan h of k d. So when k is small, this is equal to g k d k squared d, because when this is small, this is just kd. So omega squared equals g k squared d. So omega over k equals the square root of g times d. I knew it was wrong when I was coming out. So short waves are non-dispersive. because they can't really see the bottom. But they depend on the bottom, but they're not dispersive. So short waves are non-dispersive, but long waves, when this goes to infinity, then omega squared equals g times k. Now omega squared over k squared equals g over k, and the v phase is equal to the square root of g over k. So for long waves, the phase velocity decreases with wave number. So short waves have high k, so short waves make this small, so short waves go slower, and long waves go faster. Does everybody feel at least basically comfortable about that progress of events? More or less, if you want, I can go back and do any of that again. Yeah, so what do I have left? 20 minutes. And that clock is in fact correct. Okay, let's start talking about shocks. Okay, so this all is subsonic flow. So everything that we've done so far has pressure waves as carrying disturbances around. So I do something to the gas, there's a pressure disturbance and it travels. But if my flow is faster than what a pressure wave can deal with, then things will pile up. And this becomes interesting because we can show really quickly that parts of the Navier-Stokes equation are problematic and will explode if not handled properly. But that doesn't tell us whether or not all of Navier-Stokes will explode. So what's the first thing to do? So the first thing to do is to actually let's talk about the reading questions, actually. Although most of the reading questions are going to be, most of the answers to the reading questions are, I will do that in a minute. Rankine, Hugoni, and Laval, a visual example of a shock. I will show you some shocks, maybe in a minute. One of you had asked about adhesion and cohesion in Navier-Stokes. And I don't actually know how you would go about doing that. I think, so this is adding adhesion and cohesion are the intermolecular forces in the fluid itself. And I think if it's a Newtonian adhesion and cohesion, so if you push on it, it breaks apart, then Navier-Stokes is unchanged. But if the cohesion and adhesion give you non-uniform properties like shear thickening, sometimes the cohesive forces are strong and then break as you start to push on it. So that's like a shear thinning liquid. So as you push it, it flows. Paint or ketchup are shear thinning liquids. So if you can hold the ketchup bottle upside down forever, when you push on it, it flows. Though paint is not. Paint is a shear thickening liquid. So if you take a paint stirrer and you put it in a can of paint, if you put a stick on a drill, put it in a jar of paint and make it spin real fast, you can watch the paint climb up the shaft of the drill because paint is shear thickening. It gets thicker and the cohesive forces get stronger as it gets pushed on, so it starts to climb up the shaft of the drill. So if it's non-Newtonian, then you'll have other forces that you have to model. If it's just straight Newtonian, then I think that the only thing that matters is it'll affect the viscosity model, which you're modeling somewhere else anyway. The method of characteristics, did they actually do anything in this chapter? Which is a great question. I love method of characteristics. I don't really care for the book's description of it. I don't really care for any description of it. I've not read a description of method of characteristics that I like. The only way to learn method of characteristics is to beat your head against it until you break through. So we'll do that. That's the first thing we're going to do. What are the limits to Sedov-Taylor in astronomy? So Sedov-Taylor is this model of a spherical explosion. So whenever you want to know what the limits are, look at the assumptions that you make going into it. So the assumptions that go into the Sedov-Taylor explosion are that the background is uniform and not doing anything interesting, and the explosion energy is large compared to the thermal energy in in the system, and then it's basically spherical. So things that can deviate that, a supernova is basically a set-off Taylor blast wave blowing into a medium. So if you really want to do it properly, you have to take into account the actual stuff that it's exploding into, and that gets a little bit more complicated because then it's no longer time independent. It's no longer scale free. So if you take all of the boundary conditions into account, it gets a little harder. So basically, if it's not round, or if it's blowing into something, if the background medium is not uniform. Oh wait, one of you had asked. And all I wrote down was vacuum of space. So space is not a vacuum. It's because any astrophysical object is light years across. There's a lot of stuff. There's a lot of mass in a cloud of interstellar gas. Even the gas around the planet is not a hard vacuum. Well, okay, it's a hard vacuum by what I can do on Earth, but when you have a light year of this stuff, there's plenty of material and lots of sound waves travel. So you don't think about space as being empty, just thinking about it as being large. So sound waves travel perfectly fine in the vacuum of space. There's lots of sound in space. And then lots of shocks, because things move incredibly fast in outer space. I will talk about, I'm not going to get to Laval nozzles today, but I will next time. I'll show it now. I'll put stuff up now. Oh, and he talks about a shell inside the actual front. So when in the Laval, in the set-off Taylor blast wave, there is a spherical shell that's expanding. And then when he talks about shells inside, that's just a cartoon. That's just saying we're going to parameterize things by radius. Talk about shells because I don't need to talk about anything other than a shell because it's spherical. So everything is a shell. Anything that changes is a shell. It's either a shell or it's a solid. So that was just terminology. There's only one actual thin shell. Okay, so let us. I'm going to do. Actually, I'm going to. It is late in the day and there's been heavy things. Let's look at pictures. Oh, let's turn the camera on. That's not too long. Good. So, if I move my hand through the air gets out of the way. Why does the air get out of the way? Because of the pressure. There's a pressure wave. The pressure wave is launched by the surface of my hand, and it tells the air that you got to go somewhere else because I'm coming through. Now, if I do that faster than the speed of sound, then the sound wave can't tell the gas that I'm coming. So all the gas just piles up on my hand. That is, if I could wave my hand faster than the speed of sound, which is very challenging. Doing anything faster than the speed of sound is hard. What are you doing? Freaking out?
Is that what happens with the whip?
Yes. Yes, that's exactly what happens. So when you have oh, okay, cool. Good. What is that? That's not what I want. Okay, there you go. All right. Sorry, I'm gonna find all my things. Oh, there's a homework due next week, beginning of next week. The schedule is presently not in sync with what I'm actually doing, and I apologize about that. I'm going to fix it up after I'm done with class. I didn't realize that so many of you were actually planning what you're doing based on the schedule that I put up, which that's rad. So I will adjust. Normally the schedule is like, oh, I think I'm going to do these things, and then I kind of ignore it. But if you guys are actually paying attention to the schedule, I'll do a better job of keeping it up to date with what I actually think is doing. That's just an executive function that I kind of suck at sometimes. So let's look at some shocks. Can I do this? Yes, you can. It's a GIF. Oh no, that's just a PNG. Where's my GIF? Safari does, in fact. Preview also kind of sucks because Preview won't just play a GIF. You can see it in the, okay. This will launch a couple of times. So this is a supersonic projectile that is launched out of a cannon. Notice how little this thing falls. Oh yeah, you guys can't see that. Oh, thanks. Oh yeah, there you go. Let's lower that a little bit. Okay, so here we've got this supersonic projectile. It's like a flying saucer. When it goes past the background fence that has the lines on it, then you can see the shock. So it goes by really fast. There it goes. Here. And then here. It's kind of quick. Let's actually a good shot of it is here. What did I tell you? So here, so this line here is the shock. And it's happening just because this thing is moving faster than the speed of sound through the air. And so it's piling up material in front of it. It's piling up this much material as it goes through. So you can see this line because of Snell's law. So you remember Snell's law from second or third grade? Whenever you went there. Snell's law says that photons will bend based on the index of refraction, and when gas gets a little bit denser, the index of refraction changes by enough that you can measure it. So I'm doing this experiment. I'm not really an experimental physicist, but I have a couple of experiments that I'm working on that are both about supersonic fluid dynamics. And one of them is over at this supersonic wind tunnel. So we have this really great polysonic wind tunnel in the engineering department over by the Mag Lab. And they have this machine, and it's about the size of this room-ish. And there's a Laval nozzle that you read about, and we'll talk more about, but it's this big, and it goes to Mach 5. And it's very cool. And so one of the things that we're doing, so this is training data that my colleague sent me. So this is an image from the wind tunnel. If you can see all these little points in the background, what we do is, so this is a spike that is in the middle of the wind tunnel. And then the wind gets turned on and blows in, and I think this one is at Mach 2. And the spots are a printed sheet of paper on the back of the test chamber. And so photons travel from that and then get bent by the shock, and so you can see them. And I would show you what the difference between the two pictures are. Actually, maybe You can really barely tell there's a difference. Let's see if I can find it actually. Oh, that's not going to work. Anyway, you can barely tell, so I'm not going to... when the wind turns on, you can barely tell where the deviation is, but because I got a computer and the camera has got great resolution, I can figure out where the bend is, and so we can sort out where the shock is. And it looks like this. So the color shows you the displacement of the pixel. So as soon as the wind turns on, you can see the spike deviate, and then you can see this shock. And so the pixels in that picture that you saw before are deflected up by a little bit here and to the left. So we can see the shock by looking at the displacement, and by using this array of pixels, we can actually measure the density of the gas. So this is something I'm working on, is how dense is this right here? And then we're going to do it with turbulence, and then we'll learn about star formation. That's still not the right thing.
So are those other lines from like the room?
Yeah, the other lines are from the boundary of the wall.
Mm.
Let's see. How many of the rest of these are relevant? Here's a cool video on a supersonic ping pong launcher. So here's a cool paper. It's called Supersonic Ping Pong Gun. And here's their image. So this is their converging, diverging nozzle. So it's about this big. It's a thing you can do in the lab pretty painlessly. Anything else I wanted to show you guys? Well, while I have it, let's look at the Trinity test. So here's the Trinity test. So this is the first nuclear weapon that's ever been detonated in New Mexico in 1945, right?
Probably already.
Not much.
No, but
Yeah, when did World War II end? Like
45.
45. So it was like,
August 45.
yeah, it was earlier that year.
Oh.
The whole Manhattan Project was incredibly fast. They pulled the whole thing off in like 2 years. So this is that, and this is, let's see, this is the image that, does the book talk about how they published the yield of the first nuclear weapon in the on the front page of the New York Times, which is really bad. That's really classified as how big our actual biggest bomb is. But they published this image, and from this image you can sort out the actual yield of the nuclear weapon to within like 10%. Why? Because they give you the size and the time. You don't need to know an absolute scale because it's scale free. So you have everything that you need right there. But only a half a dozen people in the world could actually do that calculation at the time. I think that's all I got for today. Does anybody have any questions on anything? We'll talk more about shocks on Thursday. It's not a reading due, because that's basically what we're going to do is the reading. And that's it. Have a good day. think so.
Okay.
Yeah, I think I'm not gonna do anything that's gonna absorb my. I realized yesterday that, and this hasn't affected anything that we've done so far, but it was going to. I realized that I was building my initial conditions with this huge amount of divergence of magnetic field.
Oh.
So I had to frantically rewrite my initial condition generator. But now I have a better one, so now it'll work.
That's nice. Yeah, I figured out a basic model for input and output for the machine learning.
Oh, okay.
Like what could be